Okay, I want to finish up section 8.1 now. We're talking about the distribution of the sample mean. And again, these are the two properties that we need to know. The mean of the sample means is the same as the population mean. The standard error, that is the standard deviation of the sample means, that's where you take the standard deviation divided by the square root of the sample size. We had done problem 5 in the last video, and at the bottom of the page there was a note. It says in the demonstration that is for serum sodium levels that I had worked through in the previous video, we were assuming that the original population was in fact normal itself. Okay, I had StatCrunch draw some histograms for me, and I was able to overlay the normal distribution curve on those pictures, indicating that the data was normal to begin with. Okay, but what if the original population is not normal? Okay, what would the distribution of the sample means look like? Like, you know, in that example that I had gone through earlier, that demonstration, the serum sodium levels were already normal, so maybe it's not surprising that the distribution of the sample means was normal. Okay, like I don't know that maybe we'd be shocked about that. You know, still seeing a bell curve. What if the original population is not normal? Okay, let's take a look at another demonstration here. So problem 6, it says that a researcher with A.C. Nielsen randomly selected households and determined the number of televisions in each household. Treat the researcher's data as a population. Now, I don't have the data in front of us. That's okay. We don't need the data. All right, but I used the data to construct a histogram using StatCrunch. I did that. And what is the shape of the distribution here? Well, skewed to the right would be the best fit, right? Because the right tail appears to be longer than the left tail here. There is a bump in the graph, but the graph is not symmetric on either side of the bump like what it should look like when we have something that is normal. Okay, so this data is, I think, skewed to the right, and there's no other, you know, choice that you'd even consider. So yeah, we're looking at the number of televisions in a household. I think most households are going to have one TV or two TVs in the house. Okay, now not everyone's going to have one or two TVs. Like some have no TVs in the house, and some got to have a TV in every single bedroom, and you know, and they got like 10 TVs in the house or whatever. So so we have something that's going to produce a situation where the right tail is going to be longer than the left tail. Part B of this, using StatCrunch, I was able to obtain 100 samples from the data set, each of size n equal 5, and I had StatCrunch compute the mean each time. Okay, so I selected 5 numbers from the data set, from the population, and I found the mean, put those back. I selected 5 more numbers, found the mean, put those numbers back. I selected 5 more numbers, found the mean, put those numbers back. So I did that 100 times. Actually, I didn't do anything. I just hit a button on StatCrunch, and it gave me the results in a second. So with those 100 samples, I was able to take the 100 means and make this picture. Okay, this histogram. What is the shape? Well, it looks normal, but maybe you could make an argument that it's slightly skewed to the right. Okay, like it's not a perfect bell curve. Okay, maybe slightly skewed to the right. Okay, I've also got the mean and the standard deviation there, but if we go to the next page, Part C, using StatCrunch again, I was able to obtain 100 random samples from the dataset, each of size n equal 30. So I took 30 numbers from the population, found the mean, put those numbers back. I took 30 more numbers from the population, found the mean, put those numbers back. So I had StatCrunch do that 100 times. Okay, and with those 100 means, I then drew a histogram using StatCrunch, and I was able to overlay the normal curve on the histogram. Okay, Now, what is the shape? Well, it looks normal. Okay, again, it's not perfect, but I think it's more normal than it was when I had selected samples of size n equal 5. Okay, here's when the sample size was 5, here's when it was 30. Okay, so it looks more bell-shaped here, I think, when n is 30 compared to when n is 5. Notice that as the sample size increases, the distribution of the sample means becomes more normal. Even though the population, in this case, clearly is not normal, we said it was skewed to the right. From that, we have the central limit theorem, and it says, consider population with any shape distribution and with mean mu and standard deviation sigma. If we find sampling distributions of the mean using samples with size n from this population, then the sampling distribution of the mean will become more and more normal as the sample size increases, just like what happened here. The mean of the sample means is the same as the population mean, just as it was before, and the standard deviation of the sample means is where you take the population standard deviation divided by the square root of the sample size, just as it was before. Okay, so the note here, this is basically saying that if the sample size is large enough, then we can consider the distribution of the sample mean as being at least approximately normal. To be safe, statisticians agree that if the sample size is 30 or bigger for non-normal populations, if it's normal, then there's no problem, right? Because you're already working with the bell curve. But if it's not normal, the sample size has to be big enough, okay, at least 30 here, and you can then treat the sampling distribution of the means as being approximately normal. Okay, so let's take a look at problem 7. According to Crown ATM Network, the mean ATM withdrawal is $67 and the standard deviation ATM withdrawal is $35. Let the random variable x represent ATM withdrawal. Okay, part A, do you think that the random variable x is normally distributed? I would say no. So the mean is $67, and of course that would mean that most individuals, when they get money from an ATM, is going to be around $67. Okay. Now some people are going to go to the ATM and get a whole bunch of cash, right? They get a couple $100, and you know, but it's not possible to withdraw less than $0. So I don't think that this is going to be a bell curve, right? I don't think that the curve is going to be symmetric on either side of $67. You probably have significantly more people withdrawing less than $67 than more than $67, but you are going to have something that's skewed to the right, since the right tail would represent those individuals who are, you know, withdrawing hundreds of dollars from an ATM. Okay, so again, it's not going to look the same on both sides, is the point. Part B, if a random sample of 10 ATM withdrawals is obtained, determine, if it's possible, the probability that the sample mean is between $70 and $75. Okay, the if possible should raise an eyebrow there. This cannot be determined because the distribution is not normal. We just said in part A that it is skewed to the right, and the sample size is not big enough. Okay, the central limit theorem said that you had to have a sample that was at least 30 in order for the sampling distribution of the means to be at least approximately normal. Okay, otherwise you're not going to have that guarantee. That's what we saw in the problem here, where you know, we were looking at the number of TVs in a household. Okay, I had samples of size n equal 5. You could make the argument that this is not normal still, because, you know, the sample size is not big enough. Excuse me, I'm moving this all around. Sample size is not big enough. Okay. Part C. If a random sample of 50 ATM withdrawals is obtained, describe the sampling distribution of X bar. That is the mean withdrawal amount. Okay, well, it's going to be approximately normal since the sample size is big enough. And the mean of the sample means is going to be the same as the population mean, which is $67. The standard error would be where you take the standard deviation divided by the square root of the sample size, and that number would be roughly about 4.95. So there's not a huge spread in the sample means we would see here. Part D, if a random sample of 50 ATM withdrawals is obtained, determine if it's possible the probability that the sample mean is between $70 and $75. Okay, well again, the if possible should raise an eyebrow. Earlier it was not possible, okay, or can't be determined. Like if we were to make any calculation, it wouldn't be meaningful in Part B because the sample size was not big enough. But in Part D, we now have a sample size that is big enough, okay? Again, the central limit theorem says that the sample size has to be at least 30, and so the sample size is big enough here, for this population, which is clearly not normal. Okay, so I want to find the probability that the mean of these $50 amounts is going to be some number between $70 and $75. Let's change the variable to get our z-score. X bar minus mu sub x bar over sigma sub x bar, that would give me my z-score. And the left z-score, I'm getting 0.61. The right z-score, I'm getting 1.62 if you go nearest two digits. Of course, make sure that you're using the standard error and not the standard deviation. The standard deviation for this problem was 35. I don't want to be using that in the denominator. And again, some students will do that. They'll mess this problem up and they won't be using that correct number there in the denominator. I want to find the area between these two z-scores. In general, we got to take the area to the left of the bigger z-score minus the area to the left of the smaller z-score. All right, so let's go to the table. The area to the left of 1.62 is 0.9474, and so that's what I got. The area to the left of 0.61 is 0.7291, okay, and that's also what I had there. Subtract those numbers and you get 0.2183 is the answer to Part D. Okay, so what that means to us is if we were to randomly select 50 ATM withdrawal amounts and find the mean, we have a 21.83% chance that the mean of those 50 amounts would be some number between $70 and $75. Okay. So we are now done with what I wanted to do in Chapter 8. Again, we're only doing the one section here, 8.1. The homework in 8.1 is on page 376. Be sure to look at those problems for me.